Hello, in this video we're in the weighted least squares regression setting, and we're going to develop a test for testing estimable functions of this form, linear combinations of the beta. Now, as a reminder, the model is y is equal to x beta plus error, where the error term, or epsilon, is a multivariate normal with mean zero and variance covariance matrix sigma squared v, where v is a known positive definite matrix. Now, the weighted least squares for beta, weighted least squares estimate for beta, and I would refer you back to previous video 50 in this playlist. The playlist is Generalized Linear Models Regression. It's the 50th video. It's defined to be like this, where V is the least squares estimate, X, of course, the design matrix. So now, to conduct this test, we have to assume that this linear combination is estimable. And I have previous videos on that. If you look at, I'm going to say 53, PV 52. And so if you look at PV 52, we talk about estimability and what it means and the requirements. But it really means that this L vector can be written as a linear combination of the rows of the design matrix, okay, or in this form. So the expected value of this linear combination is this, okay? So L can be written as T prime X because it's estimable, and then beta hat is this, with Y, but we're taking expected value, so it goes into this. Now, the expected value of Y is X beta, and then this piece here is what we called A. And I would look at previous video 51 in the list. And A is is an oblique projection matrix on the column space of X. So A times X is just X, and then TX was what we were calling L. So the expected value of this linear combination is unbiased for this. Now, it's linear in the Y, so this linear combination with the weighted least squares estimate for beta hat in here is this, and so it is a linear combination of the Y's. The variance of this linear combination, and so that's the weighted least squares estimate, is this, and we really derived that in previous video 52. Then it says that this linear combination is normally distributed with this mean and this variance. And so if we subtract the mean and divide by the standard deviation, which is this, it's a standard normal distribution. Now, remember, we're in the mode to develop a test for this linear combination. And actually, with a large enough sample size, you could just use an estimate for this sigma and say, hey, this is going to be close enough to a standard normal distribution, and you can conduct tests with this. But let's derive an exact distribution. And so usually you just say, well, if we estimate this with the sample variance, then it magically turns into a t-distribution. And so, while I do think it's magical, it isn't magic. So let's divide the distributional properties of the sum of squares residual divided by sigma squared. Now, this is the true error variance. And remember, the sum of squares residuals it's just the same as the sum of squares error. Some use this, some use this. Is this. And then we derived in previous video 53 that this quantity is a central chi-squared with n minus the rank of x degrees of freedom. So a random variable would be the standard normal random variable divided by a chi-square random variable divided by its degrees of freedom. The square root of that is. So then this, when you reduce it, is this, the sigma squared and sigma cancel. and then what's left here is the mean square error. And of course we have the square root of that. So this is a t-distribution. Now there's only one part left. You can't just say, yep, t-distribution. You have to show that the numerator is independent of the denominator. And we'll do that next. But I want to show you what piece is random up here. You know, everything here is constant, 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 constant. The only random thing is the beta hat, the weighted least squares estimate for beta. And down here, the only thing random is the sum of squares residual. So we need to show that beta hat and the sum of squares residual are independent. And then we know that this is a t-distribution. So let's do that. So the numerator and denominator degrees are independent, and let's prove it. So here's the weighted least squares estimate for beta. And then this is the sum of squares residual, and we showed that in previous videos. And we need that, well, making use of the fact that y is multivariate normal with this mean and this variance covariance matrix, then showing that this is independent is much easier. Now, if you go back to previous video 51, where we showed that this is 0 and this, well, so this is an oblique projection matrix, so onto the column space of x. So ax is just x, and then ix is x, so x minus x is 0. And if we take the transpose of both sides, it's still 0. Now, if we look at this quantity here, which is this, and then we have to take the variance of y, which is this. Now I just take v, the constant sigma squared actually can be just taken out front, and it's not going to change this result. And then we take the middle piece here. If this is 0, then they're independent. Oh, and I actually have a video called quadratic independence of quadratic forms, if you want to look that up, and you can look at the theorems behind that. So here, v inverse v, that's the identity, so it goes away, and then this comes down and this comes down, but this piece right here, according to this, is 0. So that makes this whole thing 0. So that is a proof that the numerator and denominator degrees of freedom, or degrees of freedom, numerator and denominator are independent. And then it's truly a t-distribution. Now the hypothesis would be this for the estimable function is the null would be that this linear combination is equal to some value, say d, versus the linear combination is not equal to d. And we could of course use one-sided tests here if we desired, but the test statistic becomes this. Now on the random variable had L prime beta here, but under the null it's d. And so if the null hypothesis is true, this is a t-distribution, and it's probably, you know, in the middle-ish of that distribution. But if it's not d, then this difference becomes large, and then it's kind of shoved into one of the tails, into the rejection region. Now, one point that I didn't know where to put this, because all the videos are tending to be sort of long. I mean, this is a pretty in-depth topic. So I put it here. And the matrix A, which is that oblique projection matrix that we were talking about, which is part of the, it's called a hat matrix. And if you look at previous video 51, we really go into depth about this matrix A. But in this matrix, we use a generalized inverse matrix. So I want to show that A does not depend upon the generalized inverse used for here, right? And so that's what we're going to prove here. So let G1 and G2 be generalized inverse matrices of this, right? And then this right here also can be thought of as V to the minus 1/2 X transpose V to the minus 1/2 X. You know, if you kind of sort of expand that out. So let's let A1 be the hat matrix with the G1 inverse. generalized inverse in it. We're going to let A2 be the hat matrix, but we're going to use this generalized inverse matrix. So A1 is this. So this is the hat matrix. Now, normally, well, G1 is of the form this. You know, it's the inverse matrix for this matrix. But if we pre-multiply by the identity matrix, so which is this, and this v to the minus 1/2, we split it into v to the minus 1/2 times v to the minus 1/2, then that is this. So that's what we do here. And then we take one of them into here. And the reason we do that is, notice we have this matrix, which is this matrix, and this generalized inverse is of this matrix, but this matrix is this matrix, which is this matrix and this matrix. And I have a video called Generalized Inverse for a Symmetric Matrix. And if you look at Theorem 3, it says that this quantity, not the V's, but this quantity is going to be the same no matter what generalized inverse matrix you use. So this is equal to this. So if we use this generalized inverse matrix, now we pack it back together. This is the identity matrix. We can bring that back out front and we get this. Well, that's A2. So A1 is equal to A2, which says that A, the hat matrix, does not depend upon what generalized inverse matrix we use. Yep. Well, that's all I have for this video. I have one more video in weighted least squares regression. That's where we talk about the partial F tests. And then I'm going to quit. And if people want more, I'll do more, but otherwise I'm going to move on to a different topic. I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.